So, hi everyone, I'm laurieWIRED, and I'm going to be talking to you about Android Undercover. We're going to be translating some Android Java code into native code and watch how it reduces the number of AV detections. And then towards the end of this, we will take that code that we've generated and actually reverse engineer that. So we're going to be going back and forth between using kind of our black hat and our blue hat throughout this talk. So I'm going to be spending most of the time hands-on keyboard, but bear with me, I've got a few slides at the very beginning to try and give context for everybody here, for anybody who's not familiar with Android and native code and managed code. So who am I? I'm laurieWIRED, as I said, or you can just call me Laurie. I'm a reverse engineer. I specialize in cross-platform malware analysis. I also run a YouTube channel called laurieWIRED, where I focus a lot on mobile threats and reverse engineering and different techniques there. I also have a Twitter if you follow me on there. And today I'll be representing myself as an individual security researcher today. So if you're wanting to follow along, make sure you go to this GitHub right here. So it's shared in the chat. I uploaded quite a few different samples and notes that you'll be needing if you're trying and write some of the code. So it's really up to you if you feel like trying to translate some of the native code as well. I'll try and explain everything as I go through so that you could follow along if you feel like it. Or if you just want to sit back and be around for the ride, then that's totally okay. You can just watch me code as well. So let's just get right into it. These are my first starting slides, and there's not too many, so then we'll jump right on to actually writing some native code. So the only difference between this app that you see in VirusTotal, which has some different detections here for Anubis banking Trojan, and this app, which is entirely undetected, is that the second one is actually just partially written in native code. So that's the only difference between those two applications, which is what we're going to be focusing on today, using native code as an obfuscation technique. But first of all, I'm going to give you a little bit of background about what obfuscation actually is in case you're not super familiar with it. So basically, obfuscation is just any mechanism to try and obscure the underlying functionality of an application. So this isn't specific to just Android. This is common among Mac, Linux, Windows, and a bunch of different platforms as well. Actually, there we go. Let's make sure you're able to see the slides. So this is common among many different platforms, but this is particularly important for Android malware or legitimate applications, because if you're not familiar, Android is actually written in Java or Kotlin programming languages. So if you take that compiled Android binary and you throw it into a decompiler, you're going to be looking at the very pretty simple Java source code, which almost looks exactly how the developer wrote it with their original variable names and everything, so that you can actually take a look at the app and completely understand the underlying functionality. So there are offensive and defensive reasons for performing obfuscation. We're going to be looking more at the offensive way of doing this today and why we would use native code for that. But basically, this is why malware authors would try and hide the presence of additional malicious code within their application. Now, you can't simply write detections based off the presence of obfuscation within an Android application, because legitimate Android developers need to use obfuscation to try and protect their source code from people who are trying to reverse engineer it, or maybe trying to tamper with their application, or steal different data from within their application. So we have a couple ways and techniques for performing obfuscation with a lot of motivation for doing this. So let's move on to why we would use native code as an obfuscation technique. So we want to be able to hide the presence of additional malicious code within an application, and native code is really effective for doing this, because since an Android application is generally written in Java code, this is very simple to reverse engineer if you're just using one of the public decompilers like JDEX, for example. But it actually becomes a lot more challenging when you're using native code. since this is going to force reverse engineers to actually have to read the code in assembly or decompiled C code, which is a lot more challenging to understand and read. So additionally, they're going to have to understand something called the Java native interface and all of the nuances that kind of accompany this. So this takes a lot more background knowledge to be able to reverse engineer apps that contain native code. And I'll get into what the Java native interface is very shortly. So finally, another reason for using native code within an Android application is that it allows application developers to limit support for particular processor architectures. So if you're not familiar, Android devices, real devices, are usually based on a version of ARM. However, emulators are generally based on an x86 instruction set architecture. So what developers, particularly malware authors, will do is they'll actually limit support for x86 to try and prevent the Android application from running on emulators, to try and prevent sandbox applications from running the app, or reverse engineers from being able to emulate the app. So we talked a little bit about obfuscation and why we would want to use native code as an obfuscation technique, and what we can do with that, where we can limit different processor architectures. So let's look and see exactly what native code is inside of the Android ecosystem. So Android apps, as I mentioned before, are written in Java or Kotlin languages, but you can also include native binaries, which will be written in C or C++ code. So if you look on the right-hand side, we have kind of our standard application structure for an Android app, and we're defining a class in Java, and it looks like it's doing its normal Java programming, but we get this weird native keyword. So that is actually defining that this particular method will be defined within native C or C++ code. So we have our normal do something method, and that method is actually calling do something native. And that do something native is actually implemented in C++ code. If you look on the bottom there, the lib_native_lib.so is going to be containing our native C++ code, where this do something native method is actually defined. And this is going to be communicating back to our original Java class via the Java native interface. So the Java native interface isn't specific to Android. You can actually use it among a lot of different Java applications, but think of this as kind of the bridge between your managed Java code and your native C++ code. So this is going to be how they're communicating with each other. So this is going to be important when we go and actually write some code here. So make sure to remember, JNI, just think bridge between native code and Java code. All right, well, that was the obligatory background slide. Let's dive right into writing some native code. So what we're going to do today is we're going to start by putting on kind of our black hat to understand how a malware author would think if they're trying to write some native code. And we're going to be doing all of this within Android Studio. And then we're going to upload the application that we create to VirusTotal just to check and see if our native translation has successfully removed some of the previous detections that it had. And then we'll finish by going and taking on our blue hat and trying to reverse engineer that native application that we just created. And we'll be using JDEX and Ghidra to do this. So let me open up my VM here. So here is the link to the GitHub if everybody's able to follow along who wants to. And I've gone ahead and downloaded these zip files beforehand, but this is going to be the code that we're modifying today. So I'm going to open up my Android Studio, and let's start our development process. So note for today, if you're trying to follow along, this is technically taken from actual Android malware. So you may want to try running this in a VM to make sure you're not getting antivirus detections and stuff and like blacklisting yourself. But I have pretty much defanged all of this malware, so it shouldn't actually do anything malicious, but it does contain the original malicious code that was part of the Android malware source code. All right, let me open up our app. And here we go. So this is related to this partial Anubis.apk. And this is the actual source code that was used to generate this APK. So first, what I want to do is I want to demonstrate the detections that we have on this initial APK. So I'm going to look this up within VirusTotal and we'll just see what we have. So here's my SHA-256. So this is just the hash of this compiled Android application. And you see we have quite a few different detections related to Trojan, Android OS, Anubis. So what does this mean? This means that a bunch of different antivirus companies are actually detecting this Android APK. APK stands for Android Package, and this is just basically an Android application that would be running on your Android device. So Anubis is a popular banking Trojan from a couple years ago, and it tries to steal a bunch of different credentials and banking information from the victim who installs this application. It tries to spy on their SMS messages and a bunch of different things. So this represents the Anubis banking family, although there is an overall banking family that encompasses a bunch of different Android malware such as Cerberus, Godfather, and so many more. But basically, the primary goal is to try and steal banking information from the victim. So what we're going to do now is we're going to try and look at the actual source code of this as if we were the malware author here and translate some of this over to native code. So this is our main activity. This is actually not doing anything right now since I removed the functionality of calling the malicious code. So let's go over to our actual malicious class and take a look at this. So this is part of the Anubis source code that you're able to find online. And if you go through, you can see a ton of the different URLs, which is really interesting to see how this is actually developed. And as a malware author, if I was looking at this application in VirusTotal and I was like, hey, which part of this code is actually getting detected? This is the part where I would try to begin the translation to native code to see if I can remove some of the detections that are hitting on any particular bit of code. So I would go through and I might try and remove bits of code to see where the actual detections are spawning from. Now, what I've done here for this particular talk is I've actually only taken a subset of the actual malware source code so that we don't have to go through and translate the entire application over to native code, which would probably take like the entire night, which might be kind of fun, but we only have an hour, so we're just going to be looking at one particular function that will translate over to native code. So if you have opened up this APK source code, you might see this comment here, and this is the method that we have selected that we're going to try to translate over to native code. So now, if you're looking to follow along, let's actually create an entirely new project and copy this source code over to our new project and see how it works right there. So if you open up Android Studio and go File, New, New Project, you're going to have wanted to download the Android NDK beforehand, and we're going to pick native C++, and I'm just going to call this native testing, and I'm going to leave this in Java language since the code that I have shared with you is in Java, so we're not going to be using Kotlin today. We can just use the standard toolchain, click Finish. Okay, so this is going to go through and create a new Android project for us. And we need our build scripts to start working. So let's open up our source code that we're going to start translating. So this is the Anubis source right here. And these are all the classes of interest that are related to the detections that we're currently seeing from the other antivirus vendors. So we'll just give this a moment to load. Perfect. So this is our new activity, and let's just kind of take a second to look at the background and structure of a native application. So if you remember, we had our native C or C++ code that was going to be added into the overall Android application, and we used that native keyword to actually define a new method that was going to be implemented within native code. So if I'm looking over at this new Android project here, I see this public native. That is signifying to me that the implementation of this string from JNI method is actually going to be performed in our C++ code, and it's not going to be defined in Java in our main activity, for example. So where would that be if I'm developing this? It's going to be over in CPP. And then this native lib right here, and I'll double click on that. And we can actually see, if we click on this string from JNI, which is implemented in our C++ code. So another thing that we need to do if we're going to be loading in some native code is we're going to need the system.loadLibrary command. And this is actually going to take the name of that native library that has that implemented code, and it's going to import it into the current runtime of this Android application. So it's going to import this particular binary right here. Although for some reason Android Studio calls this native lib, but when you actually create the APK, it renames it to native testing. Just as a little FYI if you're getting confused about this. So let's actually port in our Android malware and start writing. So I'm going to open up, you right click, open in Explorer. This is going to open up my current directory for my source code right here. You can see my main activity right here, and I'm just going to dump the other files in because it's kind of easier to do it this way. So I'm going to copy all except the Android manifest, and let's just dump that in here. I'm going to actually skip the main activity. And now if we go back to our source over here, we should see our classes pop up. So now we have the additional malicious code that we were looking at previously. One thing to note, if you're looking at this, is you're going to need to update the package name to whatever package name you decided to name your app right here. So I'm just going to copy this, and let's go through and replace that, since it's a different package name than when I built this originally. So let's go just change this package. And we'll just go through each class. I could use like grep or sed or something to replace this, or maybe like Notepad++ since I'm on Windows. But I think there's not too many classes, so I'm just going to go through and manually paste in all of these. Looks good. Replace the package name. So the package name, if you're curious, is just kind of the unique identifier for this particular Android application, and every application has its own package name. Okay, I think I got all of them. Let me make sure my imports. Here we have a couple imports I think we need to actually modify too. Here we go. So we want to make sure that all of our application code is inside of the same package so it can find all of these different classes and activities. So here we go. We have our code, and it looks like we have everything working right now. So if I look at this is going to be the exact same code of this particular Android application right here. So if we uploaded this to VirusTotal, we would still see all of the same detections. So let's go through and see if we can't change just a little bit of this code over to native C++ code and reduce the number of detections that are hitting on this application. So I'm going to go back here. And if you're following along, I added a comment right here. We're actually going to be modifying this particular initialization data method right here. And I'm going to take this really interesting spot that has a lot of cool plain text strings from the Android Anubis banking Trojan, and I'm going to translate over this to some C++ code. So let's copy this portion. And I'll just temporarily put this over in Notepad++, since we're going to mess with this a little bit. All right, so now comes the part where we'll create a new method, and let's copy this particular method and use the same form that it is using. Okay. And I'll just fix this so it looks nice and we're able to see this. So now, if you remember, we talked previously about the Java native interface. That is related to this jni.h, and this is going to be how this utils class that's defined in Java code is going to be interfacing with this native library defined in C++ code right here. So what we want to do is we want to use this particular env pointer, which is actually pointing to the Java native interface, to actually make these method calls. So if we want to look, I'll pull up the GitHub. This is actually defining the Java native interface, which is just a structure of methods that are available within your native application. So let's make a new method that's going to perform all of these calls that we just removed in our Java code, and let's perform these over in our native code. So what we want to do is we're going to create a new native method, and how we did that before from our main activity, we're going to take this declaration right here and declare a new native method. So I'm going to define this as public native, and let's just call this set initialization. Let's just call this right here. Kind of the nice convention when you're doing this is do initialization data native, and we'll just declare that right here. So that's not defined yet. So we're actually going to go through and we're going to find this in our C++ code. And we're going to define this right here. So one thing to note is we're actually using dynamic linking for this. So in order for the runtime to actually be able to find this particular method, we need to follow this Java com example kind of fully qualified class name right here. So this is going to be the package name, followed by the class name that this method is defined in, followed by the actual method name. So the class name that this initialization data native is defined in is going to be that utils class. So let's change that right here. And this actually defines the method. So we have our method declared right here and defined right here. Let's see, we're getting some errors still. Okay, we need to make sure that we have copied all of the code. So now let's go through and let's call the Java native interface to be able to actually invoke our call from our native code. So I'm just going to leave this right here. This is going to be kind of a wrapper to show that the code actually run. And I'm going to say hello from Anubis native. And that's what we're going to be returning here. So we have our code that we want to actually translate. I'm just going to take this top method right here as kind of a reference. And let's put that in a comment right here. So now if we put this and we call this from our C++ code, we're actually going to get an error because this method is defined in Java. So the C++ code is saying, hey, I actually don't know where this method is, and I'm not sure how to call it since it's actually not defined inside of our C++ code. So that's where our Java native interface bridge comes in, so that we can use something called find class and then call void method in order to actually invoke this particular method right here. So if we go over here and we want to be able to invoke a method, I'm going to come over to my Java native interface, and we need to actually call this method through the env pointer. So if we go to our pointer and we call our call, this is actually going to show all of the different Java native interface method calls that are available to us. So we need to pick one that actually matches the method that we're trying to call here. So we're trying to call this setWrite method. So let's actually look at the implementation of this and see what it is. So I think this was void, so let's try this. Yes, so here is the actual implementation of this method that we're trying to call from native code. So you can see it's a void method and it contains 3 parameters. So let's go over here and call this. So we want to actually do env, which remember is just letting us call actual Java native interface methods from our code. We're going to do pointer, and then let's see call void method. So this is going to let us call an actual Java method from our native code. So this is going to take the object that we're going to call this on, as well as the method ID that defines which actual method that we're trying to call. So as kind of a placeholder, I'm going to name this Anubis ob, and then we'll call this Anubis method ID so that we can remember exactly what we're trying to call. So these are going to be errors at first because we actually need to call a few different methods before we're able to call this. So first of all, what is this method ID? We need to actually figure out what method we're trying to invoke via this call void method Java native interface function. So what we're going to do is we're actually going to look and we'll do J method ID, since this is the actual Java method ID of the method that we're targeting, which is going to be this setWrite call right here. And I'm going to call this Anubis method ID equals, and then remember we're using our Java native interface pointer. And then Android Studio is really nice about this. It wants us to actually get the method idea of this particular method. And it gives us kind of a preview of exactly what we're looking for, so it's nice and smart about that. So we'll do get method ID. And it's going to require the actual class that Java method is declared in, as well as the name of the target method and the signature of the target method. And I'll get exactly what the signature is in just a minute. So first of all, I'm going to say Anubis class, just as kind of a placeholder. And then this is going to be the name of the target method, and this is going to be the signature. So the name of the target method that's defined that we're trying to call is setWrite. So that's easy enough right here. So I'm going to copy that and put that in here. But now we want to actually get the signature of the method. So if we're looking at this and we had another method that was also called setWrite and it had no parameters, for example, and you were trying to overload this, then the Java native interface, even though we passed it the name of the target method, it still wouldn't know which one of these it was trying to call. So that's why we need to actually include what are the types that this method is requiring as parameters, as well as what is the return value, so we can signify exactly which target method we're trying to invoke. So what we want to do here is we want to actually encode these so that we can pass those as the signature. Now, if you're looking for a reference to what the signature is, we can actually bring up our JNI types and signatures right here in our reference. And this will tell you all of the different parameter types or return value types and what letter they actually correspond to inside of the signature if you're trying to pass that to the Java native interface. So what we need to do here is we need to say inside of this exactly what types we have. So I'm going to copy this for our reference. And let's go back to our native code. So we're going to use this for finding the signature. So it's going to go inside of parameters right here. The first is going to be the first parameter, which is this context variable right here, this particular object. So if we go over to the Java native interface, reference right here, you can see that objects require the fully qualified class name in between an L as an opener and a semicolon as a closer. So we're going to go L semicolon, and then we need the fully qualified class name of this particular object. So if we go back to utils class, we can see this is a context object, and this is part of the actual Android framework. So let's see what is the fully qualified class name of this. We can just do Android. I've actually written this one before. And let's look up our Android reference. So this is the actual fully qualified class name of this context object within the Android framework. So I'm going to copy that and put that over in our code. So this is our first type. So now for our second parameter, we actually need the fully qualified class name of the string object within Java. So we can do the same thing we did for the context object. So we'll just do this. We go to developer.android.com, and we can actually get the package name of this as well. And remember, since this is an object, this is going to go in between our L opener and our semicolon closer. And let's get rid of that. And we actually had 2 of these parameters, so I'm going to do one more of these as well. Okay, so that's our signature, except we also need to account for the return type of this. And the return type is void, so let's add a V right here. So this should be the actual full signature of this method. So you can use the nice docs online in order to find exactly which type each of these equate to. So if you look at their example here, they show you exactly how to do it. For example, if you had an int corresponds to the I, and they also have a string here, which is Java lang string inside of an L and a semicolon right there. But looks like we've got our signature now, and now we just need to continue on working backwards and finish our Anubis object right here and our Anubis class. So let's actually get a reference to this particular utils class that defines our setWrite method. So what we want to do here is we want to define another Java class. And I'm going to call this the same thing since we're working backwards. And we need to call again the Java native interface. And it's actually nice, it pops up right away for us, find class, because it knows what we're trying to do. So we actually just need the name of the class that we're trying to find. But this is again going to be the fully qualified class name. So I'm going to go over to my utils class and I'm going to grab the package name right here. So that's com, example, native testing. And these are going to be separated by slashes. So that's the package name. Now we need the class name, which was utils class. So that looks good. Looks like it didn't like our signature. Because we need to separate by slashes. So when you're using this, you actually need to do slashes instead of dots, or else it complains. There we go. So that looks good. So now we have the class where our method is defined, as well as the method ID for that. So all we need to do is actually call our Anubis object. And so if we're trying to get the current object that this has been invoked for, we need to use in Android something called the this keyword. So that's actually defined up here. So if we do this right here, we can just do this, jobj, and that is what we're going to be using and invoking here. So we can just copy that and replace that there. And it looks like we have an error. We just need a semicolon. That's how you know it's a live demo, is because we get errors of semicolons. Okay, so final thing here is we're actually going to need to pass the parameters that this particular setWrite method is expecting. So we need to pass it the context object as well as 2 strings. So if we look at all of our examples here, we're actually passing this context object and then 2 strings each time. So we need to account for that and also call that here. So if we go over to our utils class, and we go back to our original code that we were editing, we can see this context object passed right here. So what I'm actually going to do is I'm going to pass this as a parameter to our native code. So I'm going to do context. And we'll declare that right here. So this is going to be a new parameter passed to our initialization data native, which is defined over here. And we need to actually pass this as an object. And so we can include this, oops, as an additional JObject right here. So if you're writing this in C++, it's not really compatible with the Java object types. So you actually just have to declare them as JObject. And this is just saying this is a Java object, since it's not going to be compatible with a C++ object. So I'm going to call this context. Oops. Right here. So now all we need to do is pass in our context, and then the other parameters to this call void method, which is part of the Java native interface, are going to be the actual parameters that are passed to this particular method that we're trying to invoke. So we have our context, but we also need 2 additional strings. So if we were taking this as an example, we can add these strings here, but these are actually C++ type strings. So we just need to typecast these over to a JString type. So now these are going to be actual Java strings instead of C++ strings. So now it looks like we can go ahead and call our actual setWrite method right here. And it looks like everything's good, so we should just be able to edit all of these calls to match this particular format, and then we're actually able to call that Java method from our native code. So it's doing effectively the same thing that this was doing when it was written in Java, but we're declaring this over in C++ code instead, and we'll watch as that reduces some detections. So let's take the actual call here. So we have our call void method here, and we have all of this, but this was written in Java code, remember? So it's not going to follow the same kind of structure. So let's just do some Notepad++ magic and replace all of this to make it look more like this. So I'm just going to do copy right here. So we copied the context. We'll do Control F, and we'll find and replace. So we'll replace all of that here. So now remember, we also needed to typecast these strings. So let's just do a Control F like this. And let's just add a J string typecast right here. So let's replace all of these. I think that might be all. I think actually I need to go back and add a comma. I think that looks good. I think we got most of them, except there were some without spaces. Let's replace those as well. Okay, so now this looks like it's following the same structure that the native code is going to be expecting. So let's just add all of this to our code. So I'm going to copy this, and let's hope that this doesn't give us any crazy errors. We'll paste this in here. Okay, I think that looks good. So now what we're doing effectively is the same thing that this was doing over in our Java code, except we're calling all of this from native code. So you would agree that you see all of the same strings, and this is actually calling the same method that we were expecting. But this is actually being performed in C++. So let's see if we can build this. First, let me add our method call. So we'll just do our call to initialization data native, pass in our context object. So now our code should be invoked once this is actually run. So I think that looks good. Looks like we might have an error. Aha, okay. So I see this error that we're getting. It's because we didn't add the permissions inside of the Android manifest. So let me just, if we go back to our source code, I included the manifest for you as well. So we'll just edit this, and we actually need a couple permissions for the application to actually build this. So this is basically just telling the user that I require this permission to be able to send SMS right to the actual device storage and a bunch of different things. So let's paste those in and add those in our application. So that should fix that issue. I think I missed a spot. Here we go. So now this should have all of the permissions it needs to do all of its different malicious activity. So let's go to our utils class. That looks, did it fix it? We'll give it a second to update. I think it fixed it. There we go, perfect. Let's build our new application. So I'm gonna do build, and we're gonna generate an entirely new APK. So this is going to build our new application. So now we can upload this over to VirusTotal and see if our translation actually was successful. Let me see if this actually built. Nice. Okay, so it built the APK. So let's go over and locate that. So this is the new application that is partially written inside of Java native code, but has the same functionality as the original application that was fully written in Java code. So I'm going to go over and open up a new VirusTotal window, and let's see if it worked. So we can just go to VirusTotal, select new file, we'll go to the new application that we just built. And we'll select that and we'll upload and see. So let's go back to our original, had 9 detections over here. And let's let all of the different sandboxes and AVs actually analyze this. Looks good so far. All right, very nice. So we actually only have 4 detections now, and we've gotten rid of some detections from some larger antiviruses. So that looks good. So if we wanted to, we could go back throughout this application that was our malicious code, and we could start translating all of these different methods over to native code and see if we couldn't get rid of every single one of these particular detections. And actually, I think there's more detections because I've uploaded this a few times while I was testing out this particular code. So these might be written on some of the code that I was creating. So it looks like we were successful. And now we were able to remove some of those detections and have part of our code written in native, which is going to be a little bit more challenging to reverse engineer. So we're running low on time, so let's just quickly take a look at exactly how we would reverse engineer that native code. So I'm going to open this up in JDEX real quick. So this is a popular decompiler, and we can just throw this compiled application into here so we can take a look at the source code. So we'll look at our code, which was in com native testing. And this was our utils class that we were originally messing around with and trying to translate and see what it looked like. You can see we have our call to our initialization data native right here that's declared inside of this class. That was the same thing that we saw over here. Let's find that. Right here. So that was the same thing that we saw over in the actual source code that we were taking a look at. So if we wanted to, remember that this was actually defined and loaded inside of this main activity. So this native testing library is actually stored inside of the Android application as well. So this system.load library is going to look in the lib folder, and it's going to find all of the different instruction set architectures that this application actually supports to be able to run on. So if we click on pretty much any one of these, we see this lib native testing.so. So this is going to be the application that has our actual native code inside of it. So SO means shared object. This is actually just a Linux binary since Android is just basically Linux under the hood. So we can actually take this application and extract the contents to be able to get everything that's bundled up inside of our Android application. So if we look at that folder that's created there, we look at lib, this contains all of our native binaries. So if we look at ARM ABI v7, for example, which is just a particular instruction set architecture, here is our lib native testing.so. And last thing, I think, let's take a look at what this looks like in Ghidra. Okay, so let's take this native binary and we need to move this over into Ghidra. And we'll just port this and let it process it. And remember, this is a Linux binary, so .so. So this actually has the ELF header, so it stands for executable and linkable format, which is just kind of the standard Linux binary. So we'll just say OK. Then this is what we were taking a look at. And if you just double click, it will let Ghidra actually look and analyze this. So just say OK. And we will analyze this native binary. So it's in the process, and it looks a little small right here, but this is the actual code that's part of this native binary. So if you're taking a look at this, you might be thinking that, hey, this is a lot more challenging to reverse engineer than, say, this, which is the nice, pretty Java source code. So what we want to do is, if we actually want to thwart this, we can take a look at where this native method is defined inside of the native binary. So we want to go back to Ghidra and do functions. And if you remember this really long class name that we had, this javacom example, blah, 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 initialization data native, this is going to follow the same structure inside of Ghidra, so it's actually pretty simple to find. So we can do a plus here, and we'll go to the utils class. And here is all of our code that we actually wrote inside of the native binary. So if you remember, this first parameter right here is actually correctly labeled, and this is just the Java native interface environment pointer. So remember, this is the pointer that let us call all of the different methods of interest, like this call void method right here. So we can actually rename this and call this env. And then this second is actually going to be the JObject, which was, remember, the same as the this keyword. If you're familiar with Java programming, it's just pointing to the current object. And then our last argument was our context, which was used to pass to this call void method so that we could pass the necessary parameter for this set right method. So we can rename this as this JObj and kind of work backwards from here. This was context. So now if we're taking a look at this code, we can just kind of start to go through here and see for each one of these particular method calls, what the actual data that this is getting called on. So if we go to this uvar2, what is this? Okay, well, this is the method ID for this particular setRight method. So I can label this malware method ID and just go through one by one until we kind of clean this up and figure out exactly what it is invoking here. So I'm actually running low on time, but this is how you would go through and start deobfuscating the actual native part of this application as a reverse engineer. And now, as an antivirus company, what you could do to begin detecting this is actually write detections on this native.so binary instead of the Java code that was bundled into the Java executable portion of this Android application. And then you can effectively create detections for this as well, instead of just detecting if the code is actually included in Java. We can also write detections for the particular .so files. So let's go back to our slides and finish up real quick and then have time for some questions. So funnily enough, when I was working on this, I actually noticed that just the presence of native code, just including a .so file inside of your Android application, did remove some detections by different antivirus companies. So come on, AVs, do better than that. They must have some if statement saying, if.so file, I don't know how to handle this, so let's fail out. So hopefully going forward, they'll be able to account for situations like this. So real-world use cases, as you saw, it was a little bit challenging to use. You had to know the background of the Java native interface and be able to call methods by providing the method signature as well as the class, which gets a little complicated to do. So this is commonly implemented as custom packers, as it's a little bit challenging for script kiddies to use and go through and translate all of their Java code over to native code. But they can include a custom packer, which might hide different invocations of particularly important malicious Java code. So next steps, if you wanted to try your hand at this, you could take the Anubis code that is linked to in the GitHub for this particular talk, and you could try translating over some of the Java methods within it to native code and seeing if you're able to do this, as well as open this up in Ghidra and be able to reverse engineer the code that you've created. So thanks so much, everyone. I really appreciate it. I hope you learned something about the Java native interface, native code, and how you can use this as an effective obfuscation technique to hide particular malicious code in the application you're writing, or how you can actually reverse engineer code inside of a malicious application and create a detection so that you're not confused by native code.